Lab report number 1, Investigating Energy Conservation, Groups 7A and B. Introduction. The problem that we are investigating is what is the equation for kinetic energy. We went about this by comparing the calculated kinetic energies and gravitational energies to confirm that energy is conserved within the system. We predict that the gravitational energy and the kinetic energy will be very similar. Theoretically, they should be exactly the same. However, due to human error, we are expecting the numbers to be slightly off. What is energy? Energy is the capacity for doing work. Conservation of energy. In the system, energy can do two things, either transform to different forms of energy, such as heat, or transfer energy to a different system or object within the system. Kinetic energy is energy in motion, and potential energy is energy an object possesses because of its position in the gravitational field. Newton's second law is another way to know that energy is conserved. It is also known as the momentum principle, and it states that the acceleration of an object is dependent on two variables, the net force acting on the object or the mass of an object. Therefore, we get force equals mass times acceleration. Force and acceleration are directly related, and mass and acceleration are inversely related. However, force remains the same. This is another way to know energy is conserved within the system.
On slide 5, you see our system schema, which includes the ball, the person, and the ground, otherwise noted here as Earth, with the dotted lines representing everything that's enclosed within our system, and the black arrows representing forces or interactions between each object.
For scientific reasoning, we know that at the top of the height, all of the energy is gravitational energy, and at the bottom or at the floor, all of the energy is kinetic energy. In other words, energy gravitational initial equals energy kinetic final. Using this rationale and the conservation of energy, we know that the total gravitational energy we calculate will be the total kinetic energy we calculate. And our rationale for why the velocity is squared in the kinetic energy equation is in order to match the units for energy, which are kilograms meter squared over second squared. For our experimental design, we decided to investigate the conservation of energy and gravitational energy, the relationship of kinetic energy to mass and velocity, and the relationship of kinetic energy and gravitational energy. For our setup, we decided to have 3 masses, one that was 5.4 grams, 60.4 grams, and 94 grams, with a constant height. By doing this, we were able to confirm that the value of kinetic energy and gravitational energy were the same at the initial and final times. Here you can see our models. So on the left-hand side, we have our energy pie charts, and the right-hand 3 pictures are actual screenshots from the videos that we took for this experiment.
So the red arrows correlate to where the energy pie chart is and where the ball would be in the system. So at the very top, before it's dropped, we said 100% gravitational energy. At about the 1 meter point, which is about the halfway mark, we said it'd be 50% gravitational energy, 50% kinetic energy. And then at the very bottom, right before it hits the ground, we said 100% kinetic energy.
As you can see, we were able to analyze the videos from our experiment and input them into Tracker to obtain quantitative data to investigate energy conservation. First, we applied a calibration stick onto the 2 meter long stick, and then we auto-tracked the movement of the ball down the stick at consecutive points. This data was plotted along a graph and into a table. In our data, the velocities are negative, but we assume that the downward direction was positive in regards to our data. Overall, these videos that we inputted into Tracker, we were able to use the mass, height, acceleration, which was gravity, and the final velocity of the balls to solve for the potential energy and the kinetic energy. We know that through the conservation of energy, that the initial gravitational energy must equal the final kinetic energy.
In order to solve for the different energies, we simply plugged in both our measured and known values into the kinetic and gravitational energy equations and hoped to see that gravitational energy and kinetic energy would be the same.
As shown in our data, the potential energies and kinetic energies of the 3 ball drops were generally similar, and we can deduce that the differences can be attributed to errors in our calculations.
Some of the errors we believe to have happened are due to the setup of the measurement stick, the calibration of Tracker, tracking the movement unevenly when using Tracker, the ball landing unevenly between trials, an accidental force upon the ball while dropping it, and uneven heights of dropping the ball.
In conclusion, although we had some complications with tracker en route to proving the kinetic energy equation, with the data we collected, it showed the total energy stayed the same as the ball dropped, which confirmed the law of conservation of energy since the gravitational energy initial was the same as the kinetic energy final.